Welcome. In this video, we'll be discussing about linear constant coefficient difference equations again, but now we'll be looking into solving these lCCDE, basically with the help of Z transforms. So what is an lCCDE? Just a recap. So in this lCCDE formulation, you represent your output as a sum of inputs at the present moment as well as in the past instance, plus the previous outputs. So this is yn is a function of yn depends on some xn, means let's say b0 xn plus b1 xn minus 1 plus so on, all the up to m, up to capital M, be capital M, and plus some a1 yn minus 1 plus a2 yn minus 2 plus so on. So in this way, yn depends on current input and previous inputs as well as previous outputs, right? And if this system is a causal system, means it's a real world system where my xn is streaming in and my yn is evolving accordingly, and yn current value also depends on the previous values of y, right? So this is an lCCDE and it's a causal system. Now yn depends on the inputs and the previous outputs. Now let xn start from n equal to 0 and go on as it is a real world system. So basically I define n equal to 0 as my starting point, and then the system keeps evolving. Imagine if you have let's say a microphone, right? You speak into the microphone and the yn is a function of xn, and if there is some delay or if there is some distortion, then yn is a function of some previous outputs as well, right? The current output is a function of some previous outputs as well as some previous inputs as well. So this is the meaning of a real world system, that my system is a causal system. Okay, now my yn will evolve according to the previous outputs as well as the current input and the previous inputs for all n greater than equal to 0. Can you find yn? Now we have to solve the lCCDE system. If we are given xn, can we find yn? Yes, but my yn will also depend on some initial conditions, right? Because this equation, even if I know all xn for all n, which means non-zero only for n greater than equal to 0, and can I know yn? It also needs let's say if I take y0 will also depend on y of minus 1 and y of minus 2, right? So they have to be given as initial conditions. So my lCCDE system can be solved if I know my xn for all n greater than equal to 0 and the initial conditions, that what is the initial state of the system where it's starting from, right? Now if I want to take the Z transform of this system, how will it look like? I know my xn is a right-sided sequence. Similarly, my yn will be a right-sided sequence, and so the ROC should be outside the pole farthest from the origin, so that it includes the z equal to infinity, basically that infinity is included inside my ROC, region of convergence, right? Okay. Instead of looking at the general theory, which we'll be doing anyways later, but let's first consider one example, a simple example, which will help you understand how do we solve actually in general. Okay, so we have to solve for yn for all n greater than equal to 0. Consider this system when yn is dependent on yn minus 1 and the current input xn. And I have to solve this system for all n greater than equal to 0. So if I simply take the Z transform of this system, what do I get? I get y of z is a z inverse of y of z, right? A times Now, if yn has a Fourier transform yz, what will be the Fourier transform of yn minus 1? It will be 0 to the power minus 1 times yz, right? And then b times xz, right? And I can solve this for yz, take this to the other side, and yz is simply b xz upon 1 minus az inverse, right? Very simple. With the z transforms, it is so easy to solve, right? Now, let us consider a case when xn is equal to 0 for all n. Consider the case when xn is always 0. Basically, I'm giving no input. Then my xz is, of course, 0. Thus, yz will be from the previous formula, which was xz upon 1 minus az inverse, right? That will also be 0. So if my yz is 0, this implies my yn will also be 0 for all n, right? Now, go back to this equation where we have yn equal to a yn minus 1 plus b times xn. So xn is 0, always fine. But what happens at y0? When my y0 depends on y0 minus 1, basically y of minus 1. But if my initial state of my system is y1 or y minus 1 is some non-zero value, then how will the system evolve? Even if the input is 0, even when xn is 0 for all n. But if my initial condition was not 0, then the system will evolve as per this equation, which means y of 0 is a times y of minus 1. Let's say y of minus 1 is 1, then a. Y of 1, if n equal to 0, then this is y of 0 is equal to a times y of minus 1, right? And y of at n equal to 1 is equal to, this is a times y of 0, this is equal to a times a, this is equal to a square. In this way you can solve for y2, y3, and it is a square, a cube, a power 4, like that. So, but using our previous z transform based solution, I got my yn is 0 for all n. But here what I am seeing is it is not 0. Even if xn is 0 for all n, my yn is not 0. So where did we go wrong? What mistake did we do? Let's see this. There was a problem when we did the Fourier transform or the z transform. What was it? That the system was not LTI. The system is not linear time invariant. Why? Because non-zero initial conditions basically, because my y of minus 1 is not 0, so my output is non-zero even if the input is 0, right? And you know, a system is linear. If the input is 0, then y output should also be 0, right? So that is the property of a linear system, that my y is linearly dependent on x. But in this case, it is not happening. My y is not linearly dependent on x if the system has non-zero initial conditions. So this is the point. Non-zero initial conditions make the system non-LTI. Now, how do we solve it? What is the solution? So split the system into two parts. The first part is with zero initial conditions, so that my system is LTI, right? And because if my yn is 0 for all n less than 0, then my system is dependent only on xn. It is not dependent on any initial conditions, and it will follow the scaling property, right? The linear scaling property will be followed, and my system is LTI then. And the other part of the system is the response because of non-zero initial conditions. But if I consider my input to be 0, so basically the response of the system to the non-zero initial conditions, right? So this part is yn will depend on xn, and in this part my yn depends on initial conditions only, and here xn only, right? So I have two sources of disturbance to the system. In other words, what are those? One, that system was already disturbed, already non-zero initial conditions, that those disturbances will have a repercussion on the future values of the system. And the second is the system was undisturbed before, but the input is making the system disturbed. The input is making the system non-zero, right? So both these sources of disturbances, or both these sources of non-zero output, can be decoupled because it's a linear system, and they can be studied independently. And then finally, both can be added together linearly to get the final response of my system. Right? So these are the two parts. Let's look at these parts one by one. The first part is the LTI part, basically, which is because of the zero initial conditions. So my yn is a times yn minus 1 plus b of xn, where yn is 0 for all n less than 0. So this is zero initial conditions. Now define the z transform as yz is z transform of yn un. Yn, I'm saying that my yn is 0 for all n less than 0. This is because of the zero initial conditions. Right? And similarly, my xz is defined as z transform of xz un. Basically, I've already defined that xn is 0 for all n less than 0. Okay, so note this different kind of notation, slightly different script in which I have denoted this, because this is the transform not of yz but of not of yn but of yn un, right? Because zero initial conditions. So now I can apply this form to this equation, and I get yz is a times z inverse yz plus b times xz, right? And I can solve this to get yz is bxz upon 1 minus az inverse. Right? Just simply solving it, I get this. This is correct. Why? Because this system was LTI given this zero initial condition. This is an LTI system, so this is a valid solution. Okay. Now this kind of transform is called unilateral Z transform. Why? Because it considers only right half of xn or right half of yn. Means the summation yn un. So un will make my n to start from 0 to infinity, and there is z to the power minus n. So this is my y of z, the unilateral Z transform of yn. Now let's consider the other part, when the system is already disturbed and there is no external disturbance coming. So my yn is a times yn minus 1, where yn minus 1 can be non-zero for n less than 0. Basically yn minus 1, basically my y is non-zero for time less than 0. So the Z transform of this will be this. Okay, I am now considering it individually. So yz is the Z transform of yn un. So my yn un is a times yn minus 1 z to the power minus n, and because of un my limits are from 0 to infinity, right? Now if I solve this, 5 minutes later. So this is because of now I can my n starts from 0 to infinity. I can first take the zeroth term, which is y of, when n is 0, y minus 1. This, remember, this term is non-zero even if my n is, because my y at n less than 0. So this part plus the other part, which is a y n minus 1 z minus n. So here the input is basically, this is y0, y1, y2, which are anyways a part of my Z transform. Okay, so I have separated my initial condition with my evolution. So my initial condition is y of minus 1, my evolution is n greater than equal to 0, right? Now I can put n minus 1 equal to m here, and I can solve for, so ym is basically simply putting it here, I get this form, which is simply y of z times z power minus 1, right? This because of this minus 1. So I substitute it here, y of z to the power minus 1 times a, and this is the initial condition, a y minus 1. Now yz is a y minus, so I just simply solve for my yz now, which is a y minus 1 upon 1 minus a z inverse, and this is basically my z transform because of non-zero initial conditions. And now I know I have to just add both of them to get an overall response of the system. So the overall response is, this part is because of the non-zero initial conditions, and this part is because of zero initial conditions. Basically, this is because of the the input disturbance, or the input x only. This is only because of the initial conditions, and this is only because of the external input. Now, if I know xn, I can compute yn by inverse z transform, or inverse unilateral z transform, right? Let us consider one example in this regard. Let us say xn is simply a times un, and my initial condition is y of minus 1 is 2. And I solve for the same system. So if my xn is a times un, what is my x of z? X of z is simply a upon 1 minus z inverse. You remember un, the transforms to 1 minus a z inverse. And my yz, now putting it back into the formula which we derived in the previous slide, the response because of non-zero initial condition, and the response because of the external input. So b times xz upon 1 minus az inverse, right? Now, how do I solve for this? Now you know how to solve for this, right? This form is a known form. This form is product of two known forms. Basically, you can use partial fraction expansion to get the two. So this is how I use partial fraction expansion to split this term into two sum of two terms. You know how to do it. And thus, my yn is simply the inverse z transform of this part, which is simply, okay, you know, for n minus 1, it is 2. But for n greater than or equal to 0, this formulation can be used, which is 2a, and this part, the inverse z transform, is a to the power n un, a to the power n un. For this is a constant, and then for this part, the inverse transform is 1 to the power n un, so 1 to the power n, which is 1 into un, and then this part, it's a to the power n un. So this part is constant, a to the power n un. Now the un can be absorbed by this n greater than equal to 0 condition, right? So this is how I find out my y of n. So this is an example to see. Basically, whenever we have an lCCDE, to solve it, we have to consider two things. One thing is the initial conditions, the initial disturbance, which will slowly die out or amplify, whatever, which will have an effect on the evolution of system for n greater than equal to 0. And the second part is, with zero initial conditions, the effect of non-zero input. So the reference for this part is Oppenheim chapter 3 section 6, the unilateral Z transform. Thank you.